Hello, my name is Al-Magazachi, and today I will present you an application of flex technology, to be precise, rigid flex technology, in a miniaturized low-power IoT node. Let me start by saying a few words about my background. I've studied electrical engineering at the Technical University in Berlin, and I joined Fraunhofer IZM 2016 as a student. Now I am a research fellow in the department RF and Smart Sensor Systems, and my work ranges from circuit and PCB design to embedded systems programming and signal processing with higher languages. My research focus is on decentralized systems and collective intelligence, where I investigate the emergence of intelligent behavior in swarm robotic systems. My talk is relevant to those of you who are interested in using flex technology but have no experience with it. And the goal of this webinar is to give you a basis of decision-making for this kind of technology. At the end, you will have the opportunity to ask questions. The presentation is structured as follows. I'll focus on three major issues. First, I will focus on the application so that you have an example in mind when talking about the technology. And this example will accompany us throughout the presentation, and it helps to understand the decisions and the design process from the beginning to the end. Second, I will focus on the rigid flex technology itself. What is exactly rigid flex and why or when to use it? And the last part will go more into detail regarding the hardware design, what should be considered in the design, and what rules must be followed. I will finish with a short conclusion where I will give you some best practice recommendations. Okay, so let's dive in. Our real environment is more and more connected to the digital world. This idea of the interconnection between physical and digital world is called IoT, short for Internet of Things. At the core of this idea is the hardware. Once connected to the object, this hardware gives the object the possibility to perceive and to interact with its surroundings, to get connected to other devices and to the internet, and thus to become a smart device. Our application example, ZEPOWEL, short for Zero Power Electronics, was developed exactly for this purpose. It is an IoT platform with the focus, as you can see in the slide, with the focus on ultra-low power. Here in this figure you can see the energy consumption as a function of performance, and we have different platforms like for example the Raspberry Pi on the right side of the figure that has a lot of processing power and performance, but that also goes hand in hand with the energy consumption. And on the left side, as an example, the Arduino platform that has less performance but also less power consumption. And there are many other platforms platforms in between, and for example Bosch XDK or Schaeffler Optime, and our platform ZEPOWEL, as you can see in the figure, has its focus on ultra low power. So what are the requirements for this platform? As I've already mentioned, going towards zero power is one essential part to stand out from other platforms. That means we need to minimize the power consumption, we need to have an adaptive performance to minimize the device runtime, and also to maximize the device runtime, and also minimize at the same time the maintenance cycles. The second part is about covering a wide range of IoT applications. That means on the one hand we need a modular hardware where we can easily attach or separate parts or replace parts. And on the other hand, also to have flexible interfaces to easily add new extensions to it. And the third requirement is to have a reliable and miniaturized device. This is also one focus of the Fraunhofer IZM, and so that with this reliability and miniaturization we will have a device that can be easily added to already existing machines or infrastructures, and it can be easily integrated. And also to have a reliable and robust operation of the device. Okay, to further understand this platform, you can see in this slide a block diagram where you can see in the middle is the part that we call IoT core. It integrates all the important parts of which we need for an IoT platform, like a microcontroller where we perform our power management algorithms, but also a power management concept, an analog front end to integrate additional sensors, and also a radio communication. Around this main controlling part, there is a whole ecosystem of additional extension devices. For example, a solar cell or a piezo harvester, energy harvesting extensions we can use, or a battery if harvesting is not an option in your application. We have different options for communication, like wired ones like Ethernet, or also radio communication in the 2.4 gigahertz frequency range. And on the right side, you can see also different sensors we can add to the platform, like a light sensor or a temperature sensor. And the interfaces offers also many options to integrate more new sensors, actuators, and other devices. So having this block diagram and this concept in mind, the question arises of how to realize this concept. And there are different ideas how we can realize this hardware. The first option would be to make a PCB stacking. It's easy to realize by using headers in the PCBs and connecting them with each other. And it's a good option for testing and for development boards. But it's far away from being a miniaturized device and far away of being a reliable and high-quality solution. The second option is to have a wired PCB connection. It means we have these different PCBs, as illustrated on the right side, where we have connectors and cables, for example, ribbon cables, to connect the different PCBs with each other. It can be a low-cost solution, but it is this connectors and cables are also prone to errors at the connections. And the next point is that we can't have a high integration density with these connectors. So now rigid flex technology becomes interesting. This is the third option we have here. We want modularity, we want a miniaturization, we want a high quality solution with reliable connections between the boards, and this is where rigid flex comes in. In the development cycle of ZEPOWEL, we have tried all three approaches, all three concepts. You can see on the left side above this stacking solution, which we used for our development, for programming, to test the interfaces, and so for the first development stage, the stacking solution, as you can see also in the middle above, was used. It's easy to realize, but not an integrated high quality solution. On the left side above, you can see the second idea, the wired PCB connection. We have here the IoT core with its interfaces around it, where you can connect with a cable to the IoT core. And as you can see from the photos, it's also not the solution with the highest miniaturization level. So the third idea is the rigid flex, to use the rigid flex design. And we realized a rigid flex design that can be folded into a cuboid. You can see a picture above in the middle in comparison to this wired solution. You can see how significantly smaller it is, and with the connectors, with the board-to-board connectors, we can also easily add new extensions. Here are some more pictures where you also can see on the right side a comparison with a one coin euro, and also a comparison with the other solution, with the stack solution and with the wired one. Now we have this application in mind, and we want to understand what rigid flex technology is. As the name already suggests, it's a combination between rigid PCB and flex PCB. You can see the ZEPOWEL design on the right side. We have this rigid parts which we also use as a carrier for the components. There you can see the footprints of the components, and in between the darker parts are the flex parts made of polyamide materials that connects the different rigid parts with each other. There are different configurations we can combine for this rigid flex technology. We can put the flex part on the top or bottom layer outside, or even in the inner layers. There are different number also of layers for rigid and flex. And on the right side you can see, in this case, one with the flex part in the inner layers. Now the question arises, why and when to use rigid flex? For the decision making, it helps a lot to know the advantages and disadvantages. Let's start on the left side. With rigid flex, we have a higher design flexibility, so we can use this higher design flexibility to reach a higher level of miniaturization. We have a higher wiring density because we don't have any connectors or cables to connect with the PCB. So miniaturization is the first point. The second point is we can avoid additional components and assembly steps. One further point is also it's a big advantage to have a homogeneous system with a better signal integrity. It means we can ensure a reliable connection between the PCBs. And there are many other specific requirements, like we have a dynamic stable system. We have with this flex technology, we can realize components showing in different directions. This is for sensors. It's an important point, and we can use it for weight reduction. So there are some more specific requirements regarding the application. On the other hand, on the right side, you can see some disadvantages, like the technology itself is more expensive. To design the hardware, it's also, we have more consideration, it's more complicated. The number of layers is limited in comparison to standard FR4 rigid PCB design. The processing time is longer because we have additional processing steps, and of course, once designed and connected, the connection can't be separated. And the technology itself is more expensive, but it can also reduce the overall costs, especially because we can avoid, as I already mentioned, additional components and additional assembly steps. So it always depends on your case. Now let's go deeper in the design. When designing a PCB, we have to consider the bending radius. There is a formula. We can calculate the bending radius as a function of the flex thickness, and there is also a formula for the flex length. And this also depends on how you want to realize your rigid flex design in your housing at the end, in the product. How is the device folded at the end. And also for this case, there are different formulas, which you can see here on the right side. And I have also added the link in the slide so that you can look it up yourself when designing a rigid flex hardware. Also, we should, in the flex part, we should use teardrops and avoid vias in this part. And when it comes to routing, we should take care of routing in parallel and or perpendicular to the bending, so that we have a reliable traces in the design. So what does the final design look like? We have 6 rigid FR4 parts in the design. As you can see here on the left side, we have 5 flex parts that connect this flexible, that connect these rigid parts with each other. The overall size when folded is 34 by 16 by 13 millimeters. We have 58 different component types and 165, in a sum, 165 components integrated in this design. The SMD components can be assembled with a machine. We use only SMD components so that we can assemble them all by a machine and without further steps. The stack up is made of 6 different layers. We have 2 rigid parts bottom, then 2 flex parts in the middle, and 2 rigid parts again in the top layer. There are some more information about line width and space and drill, which you can see on the slide. We have solder mask on both sides and side plating, which I will show on the next slides to fix the folded module. The surface finish is nickel gold, and one point that should be mentioned is also we have an RF trace with an antenna where we have an impedance matching in this design. Okay, this is how the design looks like in a 3D rendering after designing it with, in this case, with Altium Designer. So we have the components on the inner part of the module. We have the connectors on the outer part, and you can see also the dimensions. And on the right side, you can see the antenna and programming interface. Here you can see a simulation where you can see that when the cuboid is folded, the components don't block. So this is also a point you have to consider in the design when folding, that the components don't block each other depending on your application. Now I will show you the assembly steps. So we start first with the outer layer and then with the inner layer. So we start with the connectors and then with the more complicated footprints and components. And yeah, first, on the left side, you can see the PCB without how we get the PCB from the manufacturer. The first step is a solder deposition. And after this step, we can place the components with a machine. And the third step is going through a reflow soldering process so that we can fix the components to the PCB. It follows an optical and electrical inspection, and if everything is fine, we can fold the hardware and fix them. And as you can see with the side plating, with solder, fix the board to a cuboid. And here you can see some more detailed photos with the solder to fix the device, and on the right side you can see also an extension board that is attached by the board-to-board connector. Okay, so let me sum up and give you some best practices and recommendations. You should use rigid flex technology when you want to have a higher design flexibility, so that you can, for example, place components in different directions like sensors, or if you want to have a high miniaturization, then rigid flex technology is one solution. We can also, with rigid flex technology, avoid additional components and assembly steps. We can use also rigid flex to have an homogeneous system that we can model and simulate better with a better signal integrity throughout the whole design. And this points the miniaturization to that we use only a smaller area and the avoiding of additional components and steps. This also can help to reduce the overall cost for the product, but always it depends on. And yeah, if you design rigid flex, pay attention to the stack configuration, the bending radius, flex thickness and length. There are formulas which I gave you in the slides. Take care of the routing recommendations of the parallel and perpendicular routing in the flex part, and also take care of the manufacturer specific rules. So thank you for your attention. I look forward to your questions.